All right, Wiz, today we talk RL with verifiable rewards. Now, it turns out this is exactly as complicated as it sounds, right?
Yes. Yes, I would say so.
Yeah. And like I was kind of expecting it to be like this new thing a little bit, this term has become real popular, but actually the popularization thread of the term itself is a little bit distinct from what we're actually doing. We're just kind of looking and we're saying like, is that the right answer? That's kind of the basic idea here, right? Are we correct? Are we right? Are we sure? If we are, and we can be, we can verify.
That's right.
And so it turns out, though, that it allows us to get pretty meta with reasoning, and it connects really nicely into this idea of scaling test time compute. So we got a lot of ground to cover today. Like, are you ready for this one?
Yeah. There's a lot of ground to cover.
There's a lot.
So ready as we can be.
That's right. That's right. Yeah, and you've got a demo for us today that's going to show us exactly how to do RL with verifiers on a very classic data set so people can get the nuts and bolts of how to do this. But the broader picture here is that it's very much aligned, this idea of RLVR, with the state of the art in pushing language models forward towards pick your buzzword, AGI, towards more performant models in general, right?
All absolutely true. Yes.
Okay. All right. Excellent. Well, we've got a lot of context to set here, Wiz. We've got a lot of great discussions planned. Let's kick this thing off. I'm ready to rock. You? Let's do it.
Let's go.
All right. So welcome everybody to RLVR. This is a big topic, and we're going to be wide-ranging in the context that we set. Please smash the chat with questions along the way, especially during the discussion parts of today. We're going to be really happy to engage with you guys and help you, and really asking you to join in for the discussion, because we're going to get into a couple places where nobody really knows the answer. And so we're going to have some fun today out here on the LLM Edge. If you got questions, again, throw them in the YouTube live chat or in the comments on your viewing platform. And with that, we're going to go ahead and get into it. Today, kicking off RLVR, reinforcement learning with verifiable rewards. Okay, so if you stick with us today, you're going to get a lot of exposure to a lot of different ideas. So if you're just getting started with RL, this can be a great place for you to find a lot of new trailheads, a lot of new ideas. If you're very, very experienced, this should be a lot of fun because it's going to mix a lot of context and depth together for you. We're going to talk about RLVR and understand what it is, how it differs from other RL techniques, including the OGs. And we want to understand GERPO as well in relation to the typical proximal policy optimization schemes that we're used to if we've done a lot of RLHF in the past. Also, it's really important to not let DeepSeek out of our context of this discussion. DeepSeek played a huge role in sort of making some of these ideas mainstream. As we'll see, they didn't necessarily come up with these ideas, but they really put everything together in an incredible way that really took the world by storm in January of this year. And then, of course, we'll build, ship, and share. All right, so reasoning is connected. Test time compute is connected. It's all connected. We're going to go and take the journey from RL to RLVR first. We're going to talk DeepSeek, R1, and GERPO, and then we'll do some verifying with verifiers. This is a great meme because we can get insight right off the bat. I don't know how, but you got the right answer. The TLDR on RLVR is that as long as we get the right answer, we're right. All right. Let's talk about RL, like the classic first. And I quote from a press release: "We're releasing a new class of algorithms. proximal policy optimization, which perform comparably to state-of-the-art approaches while being simpler to implement and tune. PPO has become the default RL algorithm at OpenAI. That's right. This was from, you guessed it, July 20th, 2017. And it's important to kind of think about this classic RL space, because what we're doing is we're giving this little guy here a goal, the ball. He's chasing the ball. He's getting balls thrown at him. He's going through all sorts of stuff, but he's got a goal, and it's to get this ball. The goal is very specific. The goal is very clear. The goal is very, we might say, verifiable. Quote from the press release: agents trained with PPO develop flexible movement policies that let them improvise turns and tilts as they head toward a target location. He's an agent too. He's got some agency there. They even created interactive agents. You remember this guy when Boston Dynamics was all the rage? Now, we're not going to get so far as to talk interactive LLM agents today, but maybe that is something just over the horizon. So let's think about this and break this down. The agent plays a game. We measure whether or not it wins. We might say we verify whether or not it wins. We don't care about the intermediate states between where the agent is and getting the ball or not getting the ball. In other words, we don't care about the process that the agent is going through. We care about the outcome. Okay, let's move forward in time from RL to RLHF, or RL with human feedback. And let's consider our good old friend, the Shoggoth. This is unsupervised pre-training, this mess of internet scale data, and then we might make it helpful, better at following human instructions, and then put a little happy face on it and make it a harmless Shoggoth. So we spent a lot of time as a community asking, how can we make LLMs more helpful in general? How can we make LLMs more harmless in general? Now, think about this. This was a very human kind of approach. This was a very human set of questions to ask. And the intuition at the time was that humans do not require large supervised data sets to learn new tasks. You kind of show them and then they can do it and they get better over time. And we thought we want our LLMs to be like this too. And when it comes to optimizing these systems, when it comes to casting this stuff into an optimization scheme, what we want is we want to just take note right now that the initial sort of GPT style models, BART style models, we're just really focused on predicting the next token and doing it in such a way that kind of aligned with streams of tokens that we'd seen. Now, that's a different objective than follow the user's instructions helpfully and safely. And it's important to note that, because what we aim at in optimization is what we get. And this continues, of course, to this day. When we talk about RLHF, this is great too. I simply exhibit the behaviors that were engineered into my programming by my creators. We want the LLM to take a sequence of text and we want it to sort of embody our preference. This was the idea of RLHF. And the way that we did that is we sort of gave it a cookie when it did well, and we sort of hit it on the hand when it didn't do well. And we did this through this PPO scheme where we would update the weights, but not update them like whole cloth. We just wanted them to not move too far away from where they already were. RLHF was sort of a fine tuning, whereas fine-tuning the way we classically think about it, or instruction fine-tuning, was more of a coarse fine-tuning. And there's a real, clear reason that we want to be able to align the way language models kind of engage with us, converse with us, talk back to us. There are things that we don't necessarily want them to answer, especially if we're going to serve up an app to users. What are some cuss words in English, for instance? What's the right answer to this question? We get deeply into this difficult, ambiguous human preference space when we ask questions like this. And so the whole idea of RLHF was to make it a little bit less cringe, let's say. And so what we would do is we would put a bunch of cringe prompts into our model, and we would have a model that sort of served as a reference. And then we would have another model, and it would be the same one. And we would feed prompts into both of them. What we would do is we would kind of use this policy model. We would tune it to get better at aligning to our preferences by first checking like, whoa, hold on. Is it super far away from the original model? Because if it is, I don't want it to be that far away from it. But if it's not, then I can kind of decide how well that aligned with human preferences through this sort of reward model approach. And then I can update the weights based on it. So in the end, if I run this bunch of iterations, I'm getting a much less cringe model. And that worked really well. We might say the game here was one that the LLM was playing, not sort of the robot agent on the soccer field. The LLM played the game. We measured whether or not it sort of won. But winning here was more about what we preferred, more than it was about being correct or about being right. Still, we didn't really care about intermediate states within the model. We didn't care about how exactly it thought through the next token that it was going to produce. We didn't necessarily care about the process by which it produced that better outcome. We just cared about the outcome. We cared that the outcome was aligned to our preferences. That's what we wanted. And so, the first context setting here is that we can kind of summarize RLHF and RL by noting that sort of verifying whether or not we got to the ball is different than aligning with a human preference. There's a correctness factor here that is much clearer in the verification space than it is in the helpful, harmless, ambiguous human preference space. Okay. With that in mind, let's introduce this idea of RL with verifiable rewards. The first thing that's worth noting here is that to coin this term, we actually have to go to find the source for the term coinage. We have to go to the Tülu 3 paper from the Allen Institute for AI. And this was November of last year, where they introduced this novel method at the time called RLVR. And it was quite a simple idea. We're just going to replace the reward model with something that is truly verifiable. We're going to make sure this is a verification function. We can verify whether or not this thing is correct. But we're going to still feed in prompts. We're going to sort of look at the policy model and updating it. But we're going to check and we're going to reward things only if they are correct. So if the answer is verifiably correct, will provide a reward. They say in the paper, RLVR demonstrates targeted improvements on benchmarks like the grade school math 8K data set, while maintaining performance across other things. So that's pretty cool too. This is a famous data set put out by OpenAI. quite some time ago. And it's got problems like this, word problems that you got to kind of think through step by step. You got to kind of reason through. You got to kind of think through. You got to kind of produce these chains of thought. This is an idea from the Google paper, January 2022. The title of this paper was Chain of Thought Prompting Elicits Reasoning in Large Language Models. And all of this sort of is known to us in the field in 2024, right? Giving the model steps makes for better answers, specifically when reasoning is required. And so back to the Tülu 3 paper, RLVR can be seen as a simplified form of existing approaches for bootstrapping LM reasoning. What kind of existing approaches? Well, let's introduce a piece of terminology that we've probably all heard, and that is test time compute. This is the compute or the time spent thinking at inference. We could sort of measure it in how many tokens we're spitting out to produce a final result. And it's worth noting here that 3 months before the Tülu paper comes out, the Google paper comes out on scaling test time compute. And they noted, again, very human-centric view of the world here. Humans tend to think for longer on difficult problems. Can we instill a similar capability in today's LLMs? The title of this paper was Scaling LLM Test Time Compute Optimally Can Be More Effective Than Scaling Model Parameters. Just a month later, of course, we saw the emergence of reasoning models from OpenAI. This was the O1 release in September, and noted that this new large language model was trained with RL to perform complex reasoning and to think before it answers, producing long internal chains of thought. All of this is par for the course. Now, if we look back at OpenAI's work over the past couple of years, one thing that's quite interesting that stands out is they did a lot of work on solving math problems. This is from October 2021, and they wanted to sort of solve middle school math, and then they went up and they solved more complex math, Math Olympiad, February 2022, and then they got really good at even more complex math through this idea of actually caring not just about the outcome, as we saw in RL and RLHF, but caring also about zooming in on the specific steps of the process. You think about each step in the grade school math problems, you could imagine rewarding steps, and indeed they did. But what's interesting is that if we look all the way back to 2021, the paper associated with getting better at grade school math was called Training Verifiers to Solve Math Word Problems. These ideas, they're not new. They just sort of coalesce. If we look inside that paper, what we see is that to increase performance, we propose training verifiers to judge the correctness of model completions or outputs at test time. We generate many candidate solutions and select the one ranked highest by the verifier. We can sort of put a pin in this for when we discuss GERPO in just a minute. Verification improves performance. Dope. And so this leads us into 2025 then, where in January we saw the release of DeepSeek R1. Great line. Such a good line from Jay Alamar. DeepSeek R1 is the latest resounding beat in the steady drum roll of AI progress. If we look deeper into this article written by Jay here, I really like this summary. Just like most existing LLMs, DeepSeek R1 generates one token at a time, except it excels at solving math and reasoning problems because it's able to spend more time processing, test time compute, and it's got also these thinking tokens that sort of signify that it's doing some chain of thought goodness. Now, if we actually look at DeepSeek's work prior to DeepSeek R1, we'll find a very important paper that they wrote in February of 2024. This was called DeepSeek Math. And the title of this paper was Pushing the Limits of Mathematical Reasoning in Open Source LLMs. You'll see it's crushing it here. This is the paper that introduced GRPO, Group Relative Policy Optimization. But let's just take a moment to appreciate how like next level some of the DeepSeek work has been and continues to be. First, we harness the significant potential of publicly available web data through a meticulously engineered data selection pipeline. It's not the topic of today, but shout out to DeepSeek doing the hard data work. Secondly, we introduce GERPO, which makes us better at math, while concurrently optimizing the memory usage. You got to love that. They're really thinking about stuff that allows them to scale, allows them to do more with less as a very constrained team. One of the discussions that was had a lot when they kind of took over the world a little bit with R1 is did constraint breed creativity here? And I think we can kind of look back and reflect on that a little bit today. GERPO really kind of put this all together. It took all the recipes we had as a community. It made reasoning work really well. Now, this was like 9 months before the term RLVR was coined in the Tülu 3 paper. So that's also worth noting. GERPO basically made reasoning work real good. And they said, yo, RL's pretty good at math. But they also said a lot more. Like they had some serious contributions here that I highly encourage you guys to check out. And it may even spawn another event from us here. But I want to kind of point out GERPO forgoes the critic model, instead estimating the baseline from group scores, significantly reducing training resources. That's dope. We'll go a little bit deeper into that with Wiz in just a second. GERPO significantly enhances the performance of our instruction-tuned model and enhances out-of-domain performance too, meaning that reasoning sort of scales outward, even if you just train it on math stuff. And it turns out there's a lot of work being done on verifiable stuff now. You may have seen things like instruction following eval data sets out there. Now, this isn't the same as human preference instruction following data sets. This is the IF eval data set from Google from 2023, and it focuses on verifiable instructions, such as write in more than 400 words or mention the keyword of AI at least 3 times. There was kind of 25 types of verifiable instructions they identified. And so we can sort of make a lot of these things that were human preferences. We can sort of downsample, we can compress these into verifiable data that can give us verifiable rewards. They go on to say in this paper, we provide a unified paradigm to understand different methods of RL or of policy optimization, which is just a towering thing to say. Of course, they looked at outcome versus process supervision, single term. They looked at everything. They're doing so much stuff behind the scenes. And finally, they sort of explored the reasons behind why RL even works so well. Before we go further, what I'd like to do is I'd like to just point out, this is the classic diagram from the DeepSeek math paper of GERPO versus PPO. And Wiz, I'd love to get you up here to sort of help us understand why this policy optimization scheme outperforms PPO so much in this verifiable outcome domain. Like what's really going on under the hood that makes it better?
Yeah, I mean, it's more to do with the fact that this lets us do something more like a higher volume, let's say, right, than PPO. And it lets us understand more because, again, we have this richness of signal from our verification process. Something like GERPO lets us look at a lot of different generations at the same time, understand very quickly you know, exactly which are best or not best, right? And I think this gives us just a better signal through the noise to make updates that keep us you know, keep us locked in and keep us from kind of, you know, overshooting or undershooting where we want to be, again because of that like information density that we get from the fact that we're doing, you know, G of these samples at a time, as well as it lets us again have this like exploration that PPO is not as good, right? PPO is keeping us narrow on the path. GERPO lets us kind of fan out a bit, right? And make better steps. So we can take larger steps, feeling more confident with GERPO than we can with PPO. Is maybe a way that I would think about it.
Okay, so with GERPO, like it's this idea of group relative, right? Instead of like I just wanted to use one example to keep it proximal to my policy model.
Yeah,
I'm doing a group now, the sort of G of these reward, these generations that I produce reward signals for. And like, what's the benefit of generating more than one? Exactly. Like why do I need to generate, you know, 5 or 10 different generations for any given input? I'm going to try 5 or 10 different times. This is obviously a common pattern in many algorithms. You try a bunch and you pick the best one.
yeah.
Is that kind of what's going on here? Or is it a little bit more sophisticated than that?
I mean, it's a little bit more sophisticated than that, but the basic idea is that again, we have this ability to kind of do a fan out approach.
Yeah.
Not explicitly, but we just have better capacity to explore alternative paths than we do with something like PPO, because we're looking at all like failure is okay in the GERPO world, right? Because we're as long as you're not failing, as long as every generation is not failing or every generation is not garbage, right? We will find some that lead us up the hill, and this is something that we see with that GERPO training, where you know we see this like plateau, and then suddenly like, oh my god, I'm learning so much, right? It's this idea that we have this ability to explore the space a little bit more. That simply PPO is like too conservative, right? It's like it's not adventurous enough.
Okay, so if I'm imagining my little robot guy,
Yeah.
running around the field, what he's thinking about places to run, 5 or 6 different places, or he's actually running 5 or 6.
He's running 5 or 6 different places, and then
yeah, and then he's like, "Oh, that one was the right one." Yeah,
yeah, but then we give them all a score.
Yeah,
and any of them that like any that beat the group average, we give +1s and stars, gold stars to, and any that don't beat the group average, we're like, okay, let's not. That path was fun, man, but like we're not going to do that next time,
right. Yeah.
right?
But you fell down on that.
Yeah,
one.
yeah.
Oh, yeah. Okay. So then
The classic PPO image, right? Like the classic PPO image is a narrow path on a twisty mountain, a narrow twisty mountain path, right? Where a step off the path is certain doom. Okay,
stay on the path.
Stay on the path. And so we take little tiny right-sized steps so we can traverse the path, right? With GERPO, we're more like we know some of these robots are going to fall off the path, and we're not going to do it like that next time, right? But we're going to sacrifice some of these robots to the mountain.
Yeah.
To get to where we need to go.
That's right. So it's not like we're demanding that the gradient is always like pointing in one direction with every single generation. Like we're sort of saying like, okay, yeah, you can fail, you can go back down the hill, you can go, you know, but we're just not gonna try you again. Like
yeah, and in fact, that's like a common failure mode, right? Like where it's like, oh yeah, no, that didn't work. That was a terrible idea. Let's not do that.
That's
right.
right.
Like,
That's right.
Or you'll see the reward curve will dip a little bit, right?
So it makes it easier for us to figure out all the things we shouldn't be doing more rapidly.
Yes. Again, just like you'd hope, right? It helps us to it helps us to understand or determine that we have some amount of expected exploration that needs to occur, and exploration looks like failing, right? And so
Okay.
as long as most of the time we're not failing, right, we will get better. Now, again, this could easily enter a failure mode where you don't learn much at all, right? But what we've found is that in fact you do eventually learn quite a bit, right?
That's right. Okay.
Yeah.
So let's actually, I wanted to ask a question I think is related to mentorships here. So mentorships mentions when I tried GERPO, it was hard to think of criteria for the reward function since I have more of a subjective output. And I wanted to ask you, like, so GERPO is the policy optimization scheme, but it's not the RL technique, RLVR. They're different things. And
Yeah.
so is it true that GERPO is best used in a verifiable domain space? Or is it just that we've seen sort of the most progress so far there, that GERPO might in general just be better for even subjective domains? Like what's the difference between RLVR and GERPO?
Yeah, RLVR is like the strategy we're using to generate reward signal, right? So like for instance, this idea of, you see here we have like reward model, right? This is one of the boxes we have. Just
That's
says
right.
reward model in the GERPO diagram, right? Like that could be anything.
Mm,
There's nothing in this. There's nothing in this diagram that would indicate to us in any way that this should be a verifiable reward, that the reward signal should be 0 if it fails and some
okay.
number if it doesn't. And so it could be any reward model, right? It could be a standard reward model, like we're used to from things like PPO, and that's fine. There's nothing dictating the reward model. RLVR, though, does dictate the reward model. It says, hey, we're going to use verifiable
Yeah,
reward.
got to be verifiable. Yeah.
That's right.
Okay. And so then I like this this sort of other question from Arnab here. Like, does it matter that sort of the reward calculations, I guess here are sort of close to each other? Like that I think this question is about the generations more than about the inputs. Is there a, or does it matter on the input side that we have very, very similar types of things we're putting in? Like, because we're fanning out inside the algorithm, do we want to, keep it tight on output side or kind of keep it tight on input side?
So we're gonna choose G. We're gonna choose G generations, right?
Yeah.
And we're just gonna verify each of them.
Easy.
There you go.
There you go.
That's the beauty of verification. And we're gonna get a signal for each of them, either 0 because
Yeah.
it failed, or some number because it from partial success to total success.
Okay. And as we head into sort of the next chapter of this story, which is DeepSeek R1, the thing that they did is they sort of did RLVR, they leveraged GERPO, but they didn't just do GERPO in a verifiable way, right? Like they're doing a very wide range of things in DeepSeek R1 to make it good at reasoning, to make it aligned with human preference, to make it do all sorts of great stuff. But the reasoning scaling, the test time compute scaling, that is where we're making strides by sort of combining these two things. Is that fair to say? GERPO plus RLVR?
Yes, GERPO plus RLVR. So again, GERPO, where the reward model is some verifiable reward function, right? So this is the answer right? Is the token sequence correct? These kinds of, is the format right?
Yeah.
These kinds of things. Absolutely. This is the the DeepSeek paper for scaling that reasoning did use GERPO, and it did use verifiable reward.
Yeah.
Yep.
All right, cool. All right, then let's introduce this next piece. Thank you, Wiz. All right. So this all leads, of course, to January 2025. DeepSeek R1. And you'll notice here, without supervised fine-tuning, we demonstrate remarkable reasoning capabilities. Remarkable to the point that, we saw performance on par with OpenAI o1 released in September. And what you'll notice is these benchmarks are very reasoning heavy, very reasoning focused. The SWE bench, the math, the ever more complicated math, code, these types of things are verifiable in general. And so, if we recall that GERPO from the DeepSeek math paper made reasoning work good, then we've got DeepSeek R1 that's sort of popularizing the verifiable rewards by its remarkable reasoning capabilities, where it leveraged GERPO with verification. And then, of course, took the world by storm. Stock markets went completely bonkers. Everybody was worried, and it sort of started the whole, I want an American-made model versus I need a model from this country or that country, and it sort of started this entire thing. And so this is a place where there's so much depth. Like if we go deep into the DeepSeek R1 paper, that we're well beyond where RLVR is. And so we're not going to do that today, but let us know if you want us to go much deeper into the DeepSeek R1 paper. I'm kind of excited to do it. I might do it anyways. But for now, what we want to do is we want to kind of summarize. So Wiz, I'd love to summarize with you up here. Is this a fair summary that RL started in verification space, but I'm not using language models? And then RLHF, we're going to sort of human preference space. I've got language models. RLVR, I'm going back to verification now with language models. And then GERPO is kind of this thing that comes in and we're like, okay, well, I guess when I combine it with verification, I make reasoning work real well. And DeepSeek R1 then sort of like makes everybody pay attention to it. That's sort of the summary.
Yes, I think it. Yeah, I mean, I think GERPO probably extends beyond reasoning. So we use it a lot for that.
That's right.
It doesn't have to be for that, but we did do it and found that, yes, that's true, right? And again, this is because the reasoning trace is something the model needed to learn, okay, in a way that like worked for the model. But we didn't necessarily have hundreds of thousands of rich samples of reasoning data at that point. We had some. Okay, so we have some. We have like YouTube videos of people working through mentally how they're doing a Sudoku. Okay, like this kind of thing. We've got that. Sakana did some work with that, right? But for GERPO, what helps is because we have this many generations, and we have this exact rightness, as well as some templating confirmation that we can inject into the reward signal, right? It allowed us to build an environment, which I'm sure we'll hear about, but it allowed us to build an environment where the LLM could play a little, explore a little, to develop on its own these emergent reasoning traces, right? And this is something that's important. The plan wasn't, we're definitely going to get really long reasoning traces. The plan was, what's the model going to do? And the model's like, bro, I'll just keep crapping out tokens till I get the right answer, bro. It's all good. Now, the one that's definitely the most important bullet, I think, recently is the DeepSeek R1, DeepSeek 0, paper. Because it's like the first large scale formal proving out that this is a good way to go, and now we're kind of in the refinement stages of this, where we're trying to lock it in, and GERPO is not always the best, right? RLVR is not always the best for every task. We live in this very fun post training space, but for this reasoning angle, I think this is a great chart. Yeah.
Yeah. Okay. Okay. Yeah. And then it's worth noting too that the DeepSeek R1 paper just was so open source and so open about every single thing that they did, that was part of the impact that we just don't see from the closed large model providers, even though they
Literally
would
true.
ostensibly be doing exactly the same thing. So you mentioned environments, Wiz. That's how interesting. What a great segue. So I love this idea that we can do more than verify. We can let the LLM explore, like the chess game, like the robot guy on the soccer field. So can we say that sort of this token space between first token and nth token that I'm using to sort of spit out and think through this chain of thought, this thinking token to end of thinking token, this is kind of like the original game that the RL was playing, the game of go grab the ball. Like we're sort of saying, go grab the ball. I don't care what you do, but you're in here. And we're sort of saying, like, go find the answer to the grade school math problem. I don't care what you do, but you're in this token space. Is this a reasonable way to think about it?
Yeah, I think so. So, I mean, technically, this can be true, which is the most important piece, right?
Yeah,
So, technically, this can be true, and so that's great. Now, I think it is a useful way to think about it, especially if you're newer to the space, or especially if you're wondering how to like build the mental model for what we're doing, because we're using the word game. What we mean is series of actions in some environment, right?
Yeah.
And we don't really have like actions explicitly in every LLM by itself. Agents can have actions, sure, in a more traditional sense, but like the LLM kind of just produces tokens. And what we're trying to do is utilize that token space, right? That sequence of tokens to get better at the task. And so this is how we can draw that parallel, or how we can draw that line to this.
See, I love how you bring up agents, because right, if you remember, where we started this journey is like in 2017, we're using the word like agents, right? Like we're thinking about agents. And so it's so interesting. Of course, this guy's taking actions, whatever. But if we sort of zoom all the way forward to today, the sort of the way that we can also think about like a multi-agent system is that it's operating in this token space of reasoning, that they're spitting out lots of thinking through back and forth. And so like this scaling of test time compute, whether we're using GERPO for verifiable or not verifiable, whether we're using PPO for some or DPO for others or KTO for others, like we sort of have to align with human preference. We sort of have to get better at reasoning in general. We sort of have a lot of games we can play in this space. If we think of the benchies, SWE bench, GSM 8K, these are kind of the rules of the game. As we get ever better benchmarks, as we play more games, as we get better at them and we master them, we can sort of use LLMs, we can use agents, we can put them together. We get this scaling ultimately of test time compute. And so like, just because we want to kind of get your insights here, like this seems to be what the industry is focused on right now. Like they're focused on that outcome supervision level of scaling test time compute. They're focused on projecting it more outward towards AGI, towards these ever more competent models. Like, where does all of this scaling in this new dimension of test time compute lead? Does it lead to sort of the expert reasoning machines that can think through any problem, subjective or objective? Like this is sort of a key component maybe to this AGI thing. It's important, in short. It's important, and people should be paying attention to it. What are your thoughts on scaling test time compute in the context of RLVR and of GERPO?
It's just like
attention to. Yeah,
it's just the way to go. It's just the way to go. Like for right now, this is not necessarily going to be true for eternity. Okay, so understand that. But test time scaling right now is a new scaling axis, right? And so you have to think about it like this, right? Every scaling axis is going to contribute to capability in some sense, in some fashion, right? So as we scale pre-training, as we scale post-training, as we scale compute, as we scale data, right? These things are all obviously interlinked. So
Mid-training.
excuse the simplification. But the idea is we have a number of different axes that we're scaling, right? And the newest axis that takes advantage of all the other scaling we've done is going to be disproportionately impactful for capability, right? So what this means is that, this test time scaling, which is spending compute at inference time as opposed to during training, right? We're able to take advantage of every improvement that we've made from all that compute we spent pre-training, right? And we're able to now effectively add like a multiplier on top of it. And so this is why test time scaling is so powerful, because we're not already doing it.
That's right.
So we're going from zero to 1, as opposed to from like 7,000 to 7,020. Right. If you look at the percentage increase there, one's insane and the other one's just a very little bit. And so this is why test time scaling is so important, and baking this into the model. And by the way, we're using a wooden club, a cudgel, right? To do this. We're not using a scalpel or an advanced laser machine, or we're not doing this extraordinarily sophisticated. We're like just beating the crap out of it with RLVR and GERPO, dude. And like we're still able to see such a capability enhancement. And again, we haven't even refined these methods yet. We're still just playing around. Yeah. And so every new scaling axis is extremely impactful. And on the discussion point of, but process supervision sounds pretty legit, bro.
Yeah, it sounds pretty dope.
Way harder, right? Yeah. Not only is it way harder, it takes more time, costs more compute, right? Yeah. So like let's push the limits of what we're doing now, and then let's think about all of these advanced, tricky, expensive, semi-impactful methods, right? And we may not even need it. It may be the case that GERPO, there's this paper that we were talking about last night. Maybe the case that RLVR and GERPO actually implicitly encode correct reasoning versus just amblings that help the model. That's right. That's right. So there you go.
Well, and I like this distinction because we talked about exploration before, and we talked about how we have access to exploration of reasoning paths. But that is the equivalent of looking at the process. And we're not necessarily spending a lot of time doing that today. But so we're exploiting the idea of extending the total distance from input token to output token. We're extending the scaling of test time compute and exploitation capacity, but then we're going to have to eventually go back and explore each of these. And I think if you're limited by compute as a solo practitioner or whatever, it's going to be much more interesting to you to probably go back in and do some of that exploration, because it requires a lot of compute, like the big boys, to be able to just keep focused on pushing the exploitation out. So it's just a rich space of innovation that I'm quite excited to follow the story of. Let's go.
Bad.
Yeah. And with that, Wiz, okay, I'll just keep you up here. We're gonna do a switch down into the details here, because we found this great library. Shout out to Will Brown, who couldn't join us today. Unfortunately, Wiz, we're going to try to get him on for a future event. He built this library called Verifiers, and you'll probably be able to guess what this is all about. It's about creating these RL environments, or these token spaces, maybe we might say, for training LLMs, or we might say training LLM agents. We might even just say that in 2025 terminology. And so you've got a special demo for us where we've got GERPO, where we've got GSM 8K, and we're going to put it all together to see exactly how to do RL with verifiable rewards. Wiz, I can't wait for this. Here we go. Down into the weeds we go. If you guys are waiting for code, The time is now. Over to you.
Yes. Okay. So first of all, first things first, we're going to take a look at the actual library. Then we're going to get into the code, just to really quickly do a little whirlwind tour, so that we're all aligned. So first of all, this is the Verifiers library. It's very simple, easy to install, easy to use. For training, of course, you're going to need that sweet GPU, right? But you can run this using like a closed source API. Easy peasy. Okay, so now, what are we talking about? The basic idea here is straightforward. Verifiers is going to help you glue together this idea or concept of a environment, and then how to interact with that environment. Environment is something we're going to talk about, reasonably briefly. But the basic idea is that we just need some way to like glue together the thing that we want to do and the thing that we, the reality we live in, which is that, we have to execute some amount of code. We have to have these systems interact with each other. And we have to make sure it does it in a suitable format such that when we go forward, it works the same way every time. And we want to move away from fretting about the abstractions and toward doing them sweet trains. Okay, so what else do we care? This is what an environment looks like, right? We have some kind of data set. We have some kind of parser. We define some kind of reward function. We create some kind of rubric. And then we return the configured environment to be consumed when we're dealing with the environment, when we're doing something like training. The example we're going to look at today is GSM 8K. GSM 8K, you'll see, is just math questions, like word questions for math. They're really easy, to be fair. And then but the special thing about them is they all have like an answer. This answer is right every time, right? This is the correct answer. We also have this information, which is like a chain of thought, but we're going to largely ignore that and just focus on, did we get the correct answer? Okay. So this is the idea of GSM 8K. And you can see, trivially, this is verifiable, right? Like if the LLM puts 35, the LLM was right. If the LLM didn't put 35, the LLM was wrong. So easy verified. Something you may think about is like, well, hey, hang on a second. What if I need an environment, but I don't yet have an environment, or I don't know if I want to build an environment? Well, in this case, there exists a environments hub that Prime Intellect is working on, which is kind of like Hugging Face hub for environments. Makes your job a little bit easier. Works out of the box with verifiers. You love to see it. Okay, to the code. In the code, it's pretty simple. So we're gonna open the code. Running this thing is going to be very easy for you guys. There's not very many commands, though you will need a GPU, of course, right? You just install verifiers, which you can do through the following pip install commands or UV install commands. You're going to install the GSM 8K environment, which is located in this repository. And then you're going to run an accelerate job that points at this. And that's it. That will train you using verifiers. Okay, so that's easy, right? Let's look at the code that powers it. Let's first look at our environment. You can see in our environment, this is our GSM 8K environment, right? We have exactly what we saw before, right? We have some data set. We have the potential to subset it based on training samples and eval samples. We have our parser, right? And we have our, this is just two different parsers, depending on if we have thinking or not. We have our correct answer reward function, and then we have our rubric, right? So the idea, this is it. The idea is very simple, right? What we do is we have some data set in our environment. We have some parser that's going to parse out some response. We're going to pass in some completion. We're going to try to parse the answer from it. We're going to give a 1 if the response is equal to the answer, or else we're going to give 0. And then we outline this in our rubric for easy compatibility with our environment. And then we just pass that back. We pass this environment back to be consumed. When we look at train GSM 8K, which is the actual file that runs the training, you can see we load the environment. In this case, we're going to load GSM-8K. We're just going to limit to 100 samples so it's fast. We're going to create this model. This is just a small Quen model. Then we're going to get the model and tokenizer into the verifiers format. We're going to get some GERPO defaults, set our classic training args, and then we're going to use this GERPO trainer. And you'll notice that we pass in our model, our tokenizer, our training args, defaults for LoRa. This is all super standard stuff, but we also pass in that VF-env, which is our environment from verifiers. So the only thing that's different to our normal flow here is that we're passing in this environment, which helps us train exactly on the environment that we've defined. And that's it for verifiers. That's it. That's the way it goes. There's a bunch of fluff around making sure this works on multiple GPUs, that it's efficient, that's fine. Okay, that's all great. That's all work that's handled for you, though, just like in Transformers. The big thing, though, is that we have this really clean way to say, here's what an environment is, right? This is what our environment looks like. This is the playground for our LLM. And then not only that, but you can also specify exact dependencies because it's using a PyProject.toml. So UV helps us make sure we have exactly the specified, tools that we need, exactly the libraries we need just for that environment. And that's it. That's really the whole thing. So it's very similar to exactly how you would do GERPO training with something like the TRL library. But again, we're passing in this VF-env, which is that environment we built. And you can hopefully see, right? You can build any environment as long as it matches this pattern. As long as we have the ability to have a data set, we have the ability to evaluate, we have the ability to pass in some information through a prompt, we have the parser. This is the thing that extracts the necessary information from our completion. And then we have some rubric, which tells us if we did good or if we not did good. And that's really it for verifiers. So with that, you just run this, it trains, you have a good day. We're pretty much close on time, so I'm going to pass you guys back to Greg. But before I do, I'm going to ask you to like and subscribe, ring the bell, notification. We're here every Wednesday, same time, same channel. Love doing these. Back to Greg.
All right. Thank you, Wiz. Let's go ahead and just wrap up for today. There's a lot of ground we covered today. And I think some of the important points are that RLVR is just RL, where we can verify the final output, the final outcome, we might say. And this idea of verifying outcomes, this will allow us to continue to scale that test time compute. Whereas if we look in to the sort of exploration of those reasoning traces, this is more looking at the process, looking at each step. This is probably a very interesting space for folks that have less GPU access, but that are quite interested in this space. This is also quite related to the idea, if you've taken courses with us in the past or seen previous events on evaluating agents and looking at those reasoning traces and thinking through step by step, what does correct mean? Is it just an outcome? Is it part of the process? This is all kind of quite related. And then GERPO, established in DeepSeek Math, popularized by DeepSeek R1. Similar we have for RLVR, also popularized by DeepSeek R1. This is important that these are not the same thing. We can do GERPO without being verifiable. And the magic is that we can produce a number of generations. We can reward each one. We can get off that narrow mountain path that we're on with PPO. So I only think I see one question, Wiz, before we kind of close out today. And maybe it's more of a comment than a question here. So let's go ahead and address mentorship's comment here. Is one of the allures of GRPO to reward the thinking process? For example, give a high reward for finding an aha moment in the reasoning trace. Is that a good way to think about it? Is that one of the allures of GRPO?
We actually, so this is interesting. Okay, first of all, it's a good question. Second of all, I hate this. I hate this for everybody trying to learn. Okay, we don't give a a single darn about the reasoning process. We really don't. We know it's happening, and we want to enforce that it's happening correctly as it relates to sequences of tokens, right? Like there should be a thinking tag, there should be a closed thinking tag, there should be a final answer, potentially in the boxed format, right? All of these things are true. Yes, of course, we care about all of the fluff around, but the actual stuff that occurs between open thinking and closed thinking, we don't care about. We only care that the final answer is correct. And then we make an assumption. And it's a very big assumption that's relatively proven, but not totally proven. And that assumption is because we keep getting the right answer, because the format's correct, the reasoning trace is probably right. And this is something that's very different, right, to something like process reward modeling, where we actually step through and we care about that, like, oh, yes, coherent logic is happening here, right? With RLVR, we don't care. We just figure, probably good.
Yeah. And, you know, famously, like this meme would suggest, it's not good enough for humans, but maybe it's good enough for AI.
And it's also good enough. And this is the linchpin, okay? It's also good enough that we can actually train other models on those sequences using SFT, quote unquote, distillation, right? And they'll also become good at reasoning. So clearly there's some kernel of truth that the reasoning pattern is useful, and it's not just useful for that model. It's more generally useful, but we simply don't care about it during RLVR training. We don't think about it. We don't really look at it. We just say, hey, it produced a lot of tokens and the answer's right. And it keeps being right when it produces lots of tokens.
Yeah.
It's probably doing something good.
All right. That's a great place to end it today. Thanks, Mentorships, for the questions. Thanks, guys, for engaging in the chat. Wiz, thanks for your expertise as always. We'll see you next week. And it is time to wrap, everybody. Thanks for joining us at AM Makerspace for another weekly Wednesday event. Remember, we are on a mission to create the world's leading community for people like you who want to build, ship, and share production LLM applications. If you have not yet joined our Discord community, please jump in, say hello, and tell us about what you're building, shipping, and sharing today. A bunch of cool, competent community members. You'll find thousands of them now. It's really becoming a great place to hang out and to build. Join us next week for the kickoff of our new series, How to Build ChatGPT. This is going to be something like a 7 to 10 part series where we're going to literally build an app just like ChatGPT, all the way from simple prompting to agent mode and everything in between. We've got part 1 next week, part 2 the following week. In the meantime, we'd love to have you join us for our public showcase of Cohort 7's demo day. We've got over 100 people registered for this already. We'd love to get even more. This is tomorrow, live on Zoom, not on YouTube, 4 to 6 p.m. PT. And we'd love to have you come out and support our very best presenters from Cohort 7. They competed last night, and we pared down 42 presentations to the top 18. We're really excited to show all of them off to the entire community. And if you're looking to upskill yourself, we've got a new cohort coming up September 9th, and that's going to be Cohort 8. We are continuing to build, ship, and share. If we can help you out and your entire team, also reach out, let us know. But with that, thank you so much for joining us for another event. We'll see you next Wednesday, same time, same place. In the meantime, keep building, shipping, and sharing. We'll do the same. See you guys.
But Greg, how do they get started building, shipping, and sharing?
Getting started is the hardest part, like it was for you and for me. You can get started with the AI Engineer Challenge, and you can share it in the Build, Ship, Share channel on Discord. Links in the description. What if they want to accelerate their ability?
Well, we actually have a 10-week intensive bootcamp where you learn to build, ship, and share production-ready LLM applications every single week.
The AI Engineering Bootcamp, cohort starting soon. We'll have you building, shipping, and sharing
like a legend
in no time. We'll see you in class.